We're throwing the ball up. What's our initial position? 100. I'm going to put a plus sign there just so I remember. What's our final position? 0. Our initial velocity? Upward, it's positive direction, 25 meters per second. Final velocity, we don't know. Acceleration, downward, right, 9.8 meters per second squared. So it's negative. Time, we don't know. How about our other case 2? Initial position, same, right? Final, same. How about the velocity? That's a little different, right? Because it's going in the downward direction, which is our negative direction. And V final, we don't know. That's what we're looking for. Acceleration is the same. Okay, so if what are we solving for first? Maybe V final is an easier one to solve for first. And then that way we avoid using a quadratic equation, I think, right? So if we're solving for V final, we're looking for an equation that's missing time. That would be this last one here. Oops. Okay, we can solve for V final using that because there's no time in that equation. So V final squared is V initial squared, which was, what was it? In this case, it's positive 25. And in the other case, it was negative 25. The acceleration is negative. And y final, delta is always final minus initial. So we have 0 minus 100. Okay, did you get all your minus signs right in that equation when you plugged in the numbers? So we're going to get the same thing. What do we get for V final squared? V final squared is 2585? Is that right? So what's V final equal to? You have to be careful with this equation. What's our answer have to be? Negative. Has to be negative, right? When you take the square root, it's always plus or minus, right? You need to figure out which root you're taking. In this case, we need the negative root because we know it's going downward. And what is it? It's 50.8. Did we expect them to be the same? Yes, because when you throw something up, by the time it comes back down to your hand, it's going the same speed in the opposite direction, right? We just did that. So by the time one gets back to this point, it's got V initial in the other direction, right? Or I should say minus V initial, right? It's going the opposite direction. Here, I'll write as a magnitude. V initial has the same magnitude, but the direction's down. So it's going to be the same as 2 from that point on, right? So they're going to have the same speed when they hit the ground, but the times are going to be different. So let's do, have you done the time yet? So if we're confident with our answer for v final, then we could use that. We could use any kinematics equation we want to solve for t, right? If we're not sure about our answer for v final, we can use a kinematics equation that's missing v final and solve for t, and then our answers doesn't depend on what we just did. What are we doing now? Now, if we know, I'd use the first equation, right? We know v initial, we know v final, we know the acceleration. That looks pretty easy, right? We can plug in the numbers there. So v final is v initial plus at. In this case, both the v finals are the same, right? Minus 50.8. Always use the signs properly. V initial in the first case was a positive 25. And v initial in the second case was a negative 25. And then a is the same. It's negative 9.8 in both cases. And we can solve for t. And when we do that, what do we get? 7.74. .63 seconds. Let's look at that. If you use the quadratic, so that would be y final is y initial plus v initial t plus 1/2 a t squared. You end up with t is equal to, for case 1, a negative 2.64 seconds and a positive 7.74 seconds. And for case 2, you end up with a positive 2.64 seconds, or 3. I rounded off, I guess. And a negative 7.74 seconds. It was untight. So negative time doesn't have any physical meaning here, right? So you would throw that root out and take the positive root for each one of these. But let's take a look at why, because these equations give you numbers that make sense. It doesn't know that time can't be negative, right? The math doesn't know that. So let's take a look at why it gave us those. If we plot these, let's plot, what do we want to plot here? Position. We do this all the time. You're going to do this in lab over and over again. Position versus time we'll do first. So that would be y versus t. And underneath that, we can do velocity versus time. And underneath that, we can do acceleration versus time. So what happened with this one? We gave it an initial, it starts out, where does it start out? It starts out at y equals 100, ends up at y equals 0, right? Starts out up here, ends up over here. And at some point in between, it hits its high point, I don't know, somewhere over here. It tops out, right? So it goes up, hits a maximum height, comes back down, and goes through that point there. So the curve would look something like this. This time we know is 7.74 seconds. So why did the equation also give us negative 2.64 seconds? Because if we, this is a parabola, right? So the math says, well, the parabola is going to hit the x-axis at 2 points, right? It's going to hit it over here, and it's also going to hit it over here at negative 2.64 seconds. It just fills out the parabola. And if we did the other one, it would be the exact same parabola. I could draw it over here. I need more room. Hold on. It started out the same height, but it was coming down, and it hit at 2.63 seconds or 2.64 seconds. And if we went backwards, it would have come up and this is minus 7.74 seconds over here. Okay, it's the exact same parabola. We're just picking a different part of it. We start out on this side with an initial speed that's up, right? What is speed? Speed is the slope of this graph, right? The speed at any time is the slope of the position versus time curve. So when it gets to the top of its path, right up here, what's the speed? 0, right? It's going up the second before. Right afterwards, it's going down. So at that instant, it's not moving, right? And if you look at the slope at that point, it's 0, right? It's a flat line. And the slope here, I'll draw it in blue, I guess. The slope here is a big positive number. And the slope over here is a big negative number, and they happen to be the same, right? This was a positive 25, and this was a negative 25, right? Because that's the instantaneous speed. The slope of the position versus time curve gives you the speed at that instant of the object. And so in this case, let's just quickly do this, and then we'll take a break. In this case, it starts out with a big positive speed, right? At some point, it goes through 0. Where is that point? Right here. It goes through 0, and then it ends up with a much better change my axes here. It starts out with a positive. I'm going to run out of room otherwise. Goes through 0, and then it goes through, and it keeps going. And it hits the ground right here. Okay, my scale is not very good, but you get the idea. The velocity versus time is linear. Why is it linear? Because we said that acceleration was constant the whole time. And what is the slope of the velocity versus time curve? Acceleration, right? Acceleration is change in velocity over change in time. Velocity is change in position over change in time. So that's a slope. So the slope of position versus time gives us velocity. And the velocity is changing, right? So the slope of the position versus time curve is changing. But acceleration is constant. So the slope of the velocity versus time has to be the same everywhere. That means it's a straight line, right? The slope's the same everywhere. So it's a negative 9.8. And that's the acceleration versus time graph. Okay? You could draw the two curves for the other ones also. You get, this is a straight line. You just get this portion of it. Right? It starts at, no, sorry. We're drawing velocity versus time. It started at some negative velocity, right? And it kept going So it's just this last segment here till it hits the ground at this point, right? And the acceleration, the slope there is the same as the other one. The acceleration versus time is minus 9.8. Okay?